Hello. Today we're going to talk about the essential ideas of chemistry. When we talk about chemistry, chemistry is everywhere. It's the study of matter, and matter is anything that has mass and volume. Now, mass is the amount of matter that's in an object, and it's measured in terms of grams on a balance. Volume is a measure of the amount of space an object occupies, and it can be measured in various ways depending on what the substance is. If it's a liquid, we could use a graduated cylinder, and our volume would be measured in milliliters. If it's a more regular shaped object, we could use length times width times height to figure out the volume of that object. If it's an irregularly shaped object, we can always use a process called displacement of water to find out the volume of that object. When we talk about chemistry, chemistry is a science. That means we follow the scientific method. So when we look around us, we come up with some observations, and those observations lead to questions. From there, we would do some research and formulate some kind of a hypothesis or make predictions about what the answer to our question might be. From there, we would perform experiments and collect observations. And if the results are not consistent with our prediction, we would have to start over again, form a hypothesis, perform experiments, and continue in this loop until we perform experiments whose results are consistent with our prediction. At that point, we would contribute to the body of knowledge for that particular topic. Now, if we continue to test and further testing doesn't support our hypothesis, we'd have to start over again. But if we further test and we do support our hypothesis, then much of the additional testing would yield to an observation becoming a law. And if additional testing supports the hypothesis, we may also become a theory. So when we talk about laws, scientific laws are essentially summarizations of experimental observations, whereas hypotheses tend to give explanations for the observations that were made. Both laws and theories are well substantiated, comprehensive, and testable through this whole process of the scientific method. When we talk about chemistry, we can subdivide it into three domains. Our first domain is what we refer to as the macroscopic domain of chemistry. And that's the level of what we see around us. It's the large scale observations that we can make with our eyes. The microscopic domain of chemistry is at the level of molecules and atoms. Microscopes are required to explore the microscopic domain of chemistry. And our third domain is the symbolic domain. Here, we're using conceptual representations through symbols, equations, and graphs. So let's practice the three domains of chemistry. Identify each of the underlined items as part of either the macroscopic domain, the microscopic domain, or the symbolic domain of chemistry. So if we say the mass of a lead pipe is 14 pounds, determine what domain of chemistry we're looking at. Okay, I would say that that's the macroscopic domain because we can see the lead pipe with our naked eye. If we say the mass of a certain chlorine atom is 35 AMUs, a chlorine atom is not something we can see with our naked eye. So consider what domain that chlorine atom would belong to. And we would say that that's the microscopic domain. Okay, for C, a bottle with a label that reads Al contains aluminum metal. Well, Al is the symbol for aluminum. So it would be part of the symbolic domain of chemistry. If we say Al is the symbol for an aluminum atom, again, that's going to be our symbolic domain. So now let's consider the common phases of matter. We have 3 common phases of matter: solid, liquid, and gas. When we look at a solid has a definite shape and a definite volume. Liquids take the shape of the container we put them in. They form a horizontal surface and they have a fixed volume. Gases expand to fill their container. So their volume and their shape will equal the container that they're put in. Now, if we look at solids are low energy content, whereas gases are high energy content. That means we have to add energy in to go from a solid to a liquid to a gas. So if we add energy into a solid, we're going to melt it into a liquid. If that liquid loses energy, it would go from a liquid to a solid. If we have a liquid and we add energy in, it will evaporate, so it will go from a liquid to a gas. And if we have a gas and it loses energy, it will condense to a liquid. Now, 2 other terms are sublimation and deposition. Sublimation is when a solid skips the liquid phase and goes directly to a gas. Deposition is when a gas skips the liquid phase and goes directly to a solid. When we look at plasma is a 4th phase of energy or of matter. And it's essentially a gaseous state of matter that contains electrically charged particles. And because they have their own unique properties, they can be classified as their own state of matter. Now let's move on to the law of conservation of mass. So what we're basically saying is there's no detectable change in the total quantity of matter that's present when matter is converted from one type to another. That would be a chemical change. Or when matter changes its phase, which would be an example of a physical change. Now, this is assuming that we're not talking about what happens in a star or what happens in an atomic bomb or what happens in particle accelerators where there is an exchange of matter for energy. As long as we don't talk about these types of things, matter is conserved. So practice. If we have 5 grams of ice and we were to melt it, what mass of water would we get? Well, the law of conservation of mass says that during that physical change, the matter doesn't change. So we would have 5 grams of liquid water if 5 grams of ice were to melt. If we have 500 grams of water and we were to evaporate it into steam, what would the mass be? Again, conservation of mass says that during that physical change, the amount of matter does not change. So if we start out with 500 grams of water, we would end up with 500 grams of steam. So let's say we've got 2 grams of hydrogen, and that completely reacts with 16 grams of oxygen to make water. what would the mass of the water be? Well, we're starting out with 2 plus 16. We're starting out with 18 total grams of reactant. Law of conservation of mass says we're going to end up with 18 grams of water. So now let's talk about atoms. An atom is the smallest particle of an element that has the properties of that element and can enter into chemical combinations. The concept of an atom was first presented back in 500 BC by Leucippus and Democritus. Through the years, that general concept of an atom was formalized, and John Dalton came up with what's called the atomic law in the 1800s. Now, atoms are really small. To give us an indicator of that, if we were to look at the width of a spider web, it would have 600 atoms of carbon in that one thread in that spider web. Atoms are rarely found as collections of independent atoms. The noble gases can be independent atoms. Okay, they're found on the last column all the way over on the right on the periodic table. Some atoms form diatomic elements or polyatomic elements. So examples of that might be hydrogen, oxygen, and nitrogen that all form diatomic elements, and phosphorus and sulfur that form polyatomic elements. Most atoms are found in complex structures like diamond and silver crystals. So after atoms, we have what are called molecules. A molecule consists of 2 or more atoms joined by strong forces called chemical bonds. We can think of atoms in a molecule a lot like soda cans in a six-pack. That six-pack of soda cans acts as a unit. Molecules act like a unit. Molecules can be simple and contain few atoms, or they can contain dozens or thousands of atoms. So glucose is C6H12O6. It contains 6 carbons, 12 hydrogens, and 6 oxygens. DNA contains hundreds or thousands of carbon, hydrogen, oxygen, nitrogen, and phosphorus atoms. Water is H2O, so it contains 2 hydrogens for every 1 oxygen. Carbon dioxide contains 1 carbon for every 2 oxygens. So if we look here, we've got a cotton ball. And then if we look through an optical microscope, we can see an individual fiber. If we use an electron microscope, we can see even more details within that fiber. And then at the atomic level, we can talk about what that cotton fiber would look like. Now, when we look at matter, we can classify it into several different components. So we ask ourselves, does that matter have a constant property and composition? If the answer to that is no, it's considered to be a mixture. If the answer to that is yes, we would call it a pure substance. Now, if matter does not have a constant property and composition, it's a mixture. The next question we would ask is it uniform? If it's uniform throughout, we would call it a homogeneous mixture. If it's not uniform within, we would call it a heterogeneous mixture. Now, if matter does have constant properties and compositions, then it's a pure substance. And we would ask ourselves, can it be Simplified chemically, if the answer is no, it's an element. If the answer is yes, it's a compound. So if we look here, this is an example of a heterogeneous mixture. If we look in closer, we can see the different components. It's not uniform throughout. If we were to look here, we're looking at a homogeneous mixture. It looks uniform throughout the mixture. Now, for elements, hydrogen, oxygen, phosphorus, and sulfur are all examples of elements because they cannot be simplified chemically. Water, carbon dioxide, and glucose are examples of compounds because they can. A pure substance has a constant composition. So pure substances that cannot be broken down into simpler forms are called elements, and there are about 100 of them. Pure substances that can be broken down chemically are called compounds, and there are billions of them. Now, mixtures are two or more types of matter that are blended together, and their composition varies. Also, they can be separated by physical means, like evaporation or filtration. A mixture that's composed of various points is called a heterogeneous mixture, whereas one that is uniform throughout is called a homogeneous mixture or a solution. So, oxygen, is it atomic, molecular, or elemental? So, what does a bottle labeled oxygen actually contain? Well, oxygen is considered to be a diatomic element, which means it's found as O2 diatomic elements. So, why isn't it called a compound or a mixture, a compound or a molecule? Because oxygen is never found by itself, it's always going to find something else to react with. Oxygen in a pure bottle only has other oxygen atoms to react with, so it's in the form of O2. Other diatomic elements: hydrogen, nitrogen, fluorine, chlorine, bromine, and iodine. And we can find them here. Hydrogen's here, and then nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. They kind of make a 7 right in along here. A physical property is a characteristic of matter that's not associated with a change in its chemical composition. So examples might be density, color, hardness, melting and boiling point, and electrical conductivity. All of these properties are not associated with any type of chemical change. Physical properties are properties that describe the ability of a substance to change from one type of matter to another. So examples might be flammability, toxicity, acidity, or reactivity. And there are many different types of reactivity, including things like combustion, rusting, decomposing, rotting, and digesting. So let's say we look at a candle and we melt the wax in that candle. That would be an example of a physical property, because when the candle goes from being a solid to a liquid, it doesn't change its chemical composition. But if we were to burn that wax, now we're going to change the chemical composition of that wax when it comes in contact with the oxygen and burns. So that would be an example of a chemical property. So if we were to look at rust, a physical property of rust is that it's red. The chemical property is when iron turns to rust when it comes in contact with oxygen. So here are some more examples. If we were to take copper and add it to nitric acid, it's going to produce copper nitrate and a brown gaseous nitrogen dioxide. Since we're producing new things different from what we started out with, that would be a chemical property. If we were to look at burning a match, the cellulose in that wood reacts with oxygen from the air and produces carbon dioxide and water. Even cooking has to do with chemical properties. There are many chemical changes that take place when we cook food. If we were to talk about red meat, when we cook red meat, the oxidation of iron in the myoglobin of the muscles results in that familiar red to brown color change. And even when a banana turns brown, that's an example of a chemical substance or chemical change because we're producing new substances. So next we want to differentiate between extensive and intensive properties. Extensive properties depend on the amount of matter that's present. So things like mass and volume are considered to be extensive properties. If we were to talk about intensive properties, these are properties that do not depend on the amount of the matter that's present. So things like temperature and density are examples of intensive properties. So are all elements different? Yes, they are. Okay, all elements have unique chemical and physical properties. But there are similarities in the way they behave. And that's how we come up with the periodic table.